In 1700, a massive 9.0 plus magnitude earthquake and tsunami struck the Pacific Northwest, leaving behind a centuries-old mystery. With no written records from local indigenous peoples, the disaster's cause remained unknown. Ghost forests, buried sand layers, and records of strange waves in Japan hinted at a catastrophic event, but the puzzle was incomplete. Scientists eventually solved the mystery using tree ring analysis, soil studies, and seismic data, uncovering the Cascadia Subduction Zone as the culprit. This earthquake wasn't just a local disaster. It revealed the immense hidden power beneath the earth, a force that could strike again. The 1700 Cascadia earthquake was one of the most powerful natural disasters in recorded history, forever altering the Pacific Northwest. Its 9.0 plus magnitude tremors and resulting tsunami destroyed coastlines, reshaped landscapes, and devastated indigenous communities. Beyond the immediate damage, the event revealed the seismic threat posed by the Cascadia Subduction Zone, a 700-mile fault line capable of unleashing catastrophic earthquakes. Why does this matter today? Because the fault line remains active, and scientists warn that another megaquake could occur at any time. With millions of people now living in the region, a similar event would have devastating consequences, including widespread destruction, loss of life, and economic collapse. Coastal cities like Seattle, Portland, and Vancouver are particularly vulnerable, as are low-lying areas prone to tsunamis. Understanding the 1700 earthquake isn't just about uncovering the past. It's about preparing for the future. Scientists have used the event to model potential impacts of the next big quake, driving advancements in seismic monitoring and early warning systems. Communities are building tsunami evacuation towers and updating infrastructure to withstand tremors. The 1700 Cascadia earthquake serves as both a historical lesson and a critical reminder of the region's ongoing seismic risks. The 1700 Cascadia earthquake remains one of history's most intriguing natural disasters, not only for its sheer magnitude, but also for the lack of written records from North America. At the time, indigenous communities inhabited the Pacific Northwest, passing their knowledge through oral traditions rather than written documentation. This cultural difference left scientists centuries later with no detailed accounts of the event from the region. Despite the absence of written records, indigenous oral histories provided invaluable insights. Many stories from tribes such as the Quileute, Makah, and Yurok describe a great shaking of the earth, massive waves swallowing villages, and survivors fleeing to higher ground. These accounts align eerily with what scientists now know about the 1700 earthquake and tsunami. The lack of written documentation posed significant challenges to understanding the disaster's scale and timeline. Clues instead came from nature. Ghost forests, stands of dead trees killed by saltwater intrusion, lined the coast, and sediment layers revealed evidence of ancient tsunamis. Across the Pacific, written Japanese records describe mysterious tsunami waves striking their shores in January 1700, offering a key piece of the puzzle. By piecing together indigenous oral traditions, geological evidence, and Japanese records, scientists uncovered the full story of the Cascadia earthquake. Though the Pacific Northwest lacked written documentation, the physical and cultural remnants of the event provided a profound understanding of one of the largest quakes in history, emphasizing the importance of multiple sources in reconstructing the past. In the absence of written records about the 1700 Cascadia earthquake, natural clues helped scientists piece together what happened. One significant piece of evidence was the ghost forests, areas where trees stood dead in place. These trees had been killed by saltwater flooding caused by the earthquake and tsunami. The rise in seawater triggered by the quake led to the death of these trees, leaving behind a clear sign of the event. Soil layers also provided important clues. Layers of sand were found buried beneath wetlands, likely left behind by the tsunami that washed through the area. These sand layers marked the point where the waves reached. Soil samples taken from various locations along the coast showed disturbances in the sediment, indicating a major event that occurred around 1700. Additionally, tree ring analysis helped confirm the timing of the event. Many trees showed signs of stress or sudden death around that time, supporting the idea that the earthquake and tsunami occurred in 1700. Together, these clues from nature, dead trees, soil layers, and ghost forests, helped build an understanding of the disaster, providing evidence where written history was absent. The role of international collaboration was crucial in solving the mystery of the 1700 Cascadia earthquake. While the event had no written records from the Pacific Northwest, Japanese tsunami records provided an important link. In Japan, historical records documented a large tsunami that struck their coast in January 1700, without an associated earthquake. These records were often dismissed as anomalies until scientists made the connection to the Cascadia earthquake. Researchers noted that the timing of the tsunami waves in Japan coincided with the suspected timing of the 1700 event along the Cascadia Subduction Zone. The idea that the Cascadia earthquake could have triggered a tsunami that traveled across the Pacific Ocean was initially met with skepticism. However, as scientists studied the records more closely, they began to see a pattern. The tsunami described in Japan appeared to be too large and too sudden to have been caused by anything other than a distant earthquake. By cross-referencing the Japanese tsunami accounts with geological evidence from the Pacific Northwest, including the ghost forests and soil layers, researchers were able to confirm that the Cascadia earthquake was the source of the Japanese tsunami. This international collaboration, linking Japanese historical records with physical evidence in North America, was a key breakthrough in understanding the event. It showed how vital global cooperation and sharing of data were to solving complex historical mysteries, especially when local records were scarce or non-existent. Tree ring analysis played a key role in determining the exact year of the 1700 Cascadia earthquake. Trees, especially those in coastal regions, are sensitive to environmental changes, and their growth rings record various stressors such as changes in water availability, temperature, and soil conditions. When the earthquake struck, it triggered a massive tsunami that flooded coastal areas, causing salt water to intrude into the soil. This sudden shift in the environment would have stressed the trees, causing visible changes in their growth patterns. Researchers studied the tree rings of ancient trees that survived in areas affected by the tsunami. By looking for distinct patterns of stress, scientists were able to pinpoint the year when the trees experienced these environmental disruptions. These patterns revealed that the trees showed signs of distress in the winter of 1700, which aligned with the suspected timing of the earthquake and tsunami. Tree ring analysis provided a precise way to date the event, as it allowed scientists to identify the exact year when the trees were affected by the saltwater surge. This method was important because it helped confirm that the Cascadia earthquake occurred in 1700, filling in the gap left by the lack of written records. The clear and consistent patterns in the tree rings across different locations along the coast reinforced the evidence from other sources, such as soil layers and historical records, solidifying the timeline of the disaster. Sediment and soil layers provided important evidence of the seismic activity and tsunamis associated with the 1700 Cascadia earthquake. These layers, found in wetlands and coastal areas, revealed disturbances in the Earth's natural sedimentation process, pointing to a major event that occurred around the time of the earthquake. In particular, scientists discovered sand layers buried beneath the surface in areas where the tsunami's waves had reached. These sand layers, often referred to as sand sheets, were deposited by the violent surge of seawater triggered by the earthquake. The fine sand from the tsunami wave mixed with the existing soil and was quickly buried by other natural processes. These sand layers serve as a clear marker of the tsunami's impact and help establish a timeline of the event. Soil cores taken from various locations along the coast revealed similar disturbances. In many places, the natural layers of sediment were disrupted, with a clear boundary marking the point of the event. These disruptions were consistent with the timing of the 1700 earthquake, further confirming the magnitude of the disaster. The study of these sediment and soil layers allowed scientists to establish that the earthquake triggered not only ground shaking, but also the powerful tsunami that affected the region. By examining these layers, researchers were able to gain valuable insight into the scale and timing of the disaster, using physical evidence to complement other sources of data, such as tree ring analysis and oral histories. If you have made till this far, then like and subscribe to TimeTales. Groundbreaking discoveries in the study of the 1700 Cascadia earthquake have confirmed the role of the Cascadia Subduction Zone, CSZ fault in triggering the disaster. The CSZ is a major fault line where the Juan de Fuca plate subducts beneath the North American plate off the Pacific Northwest coast. For years, scientists suspected that this fault was responsible for large-scale seismic events, but the 1700 earthquake provided the first clear confirmation. Geological evidence, such as the sand layers and disrupted soil found in coastal areas, pointed to a massive earthquake that could only be caused by a major fault zone. The size and distribution of these layers indicated an event that was larger than typical earthquakes, leading scientists to focus on the CSZ. The magnitude of the quake, estimated to be 9.0 or greater, matched what would be expected from a fault as large as the CSZ. One of the most groundbreaking discoveries came from the study of underwater sediment cores taken from the ocean floor near the fault. These cores showed evidence of sudden ground movements, similar to the disruptions seen on land. The discovery of fault line offsets and the identification of subduction zone activity beneath the ocean confirmed that the CSZ was indeed responsible for the 1700 event. Additionally, advances in seismic imaging technology allowed scientists to better understand the fault structure and its potential to produce future earthquakes. These discoveries have been crucial in understanding the risk posed by the Cascadia Subduction Zone, emphasizing the importance of preparedness for future seismic events. The potential for another megaquake in the Cascadia region remains a significant concern. The Cascadia Subduction Zone, CSZ, where the Juan de Fuca plate meets the North American plate, has the capacity to produce earthquakes with magnitudes of 9.0 or greater. Scientists have long warned that this fault is capable of triggering another massive earthquake similar to the one that occurred in 1700. The region is densely populated, with cities like Seattle, Portland, and Vancouver situated near the coastline. These areas are vulnerable not only to the shaking from an earthquake, but also to the tsunamis that would follow. The 1700 earthquake was a reminder of the destructive potential of this fault, and the ongoing seismic activity in the region serves as a reminder that another megaquake could happen at any time. Recent studies show that the tectonic plates along the CSZ are slowly building up stress, and when this pressure is released, it could result in another major earthquake. The uncertainty of when this will occur makes preparedness essential. The risk of a repeat disaster has prompted local governments to improve infrastructure, implement tsunami warning systems, and increase public awareness. Understanding the risks associated with the CSZ is crucial for ensuring that the region is prepared for the next major seismic event, whenever it may occur. In response to the seismic risk posed by the Cascadia Subduction Zone, significant preparedness efforts have been made to reduce the potential impact of a future megaquake and tsunami. One key development is the creation of new tsunami models that help scientists predict the behavior of waves following an earthquake. These models simulate the height, speed, and reach of tsunami waves, providing crucial information for evacuation planning and early warning systems. By using these models, authorities can more accurately identify which areas are most at risk and prepare appropriate responses. Additionally, evacuation towers have been built along the coast to provide safe refuge for residents in the event of a tsunami. These structures are designed to withstand the forces of a large earthquake and offer elevated safety for people who may not be able to reach higher ground in time. They are part of broader infrastructure efforts to enhance disaster resilience in coastal cities. Public awareness campaigns have also been crucial in educating residents about the risks and appropriate actions during a tsunami or earthquake. Schools, businesses, and local organizations are involved in training programs and drills to ensure that communities are well prepared. By combining advanced technology, infrastructure improvements, and education, these preparedness efforts aim to reduce the potential loss of life and damage when the next seismic event occurs. Advances in seismic monitoring and prediction technology have played a crucial role in enhancing preparedness for earthquakes, particularly in the Cascadia region. Modern seismic networks now use an array of sensors, including seismometers and GPS stations, to continuously monitor ground movement and detect early signs of seismic activity. These sensors are strategically placed along fault lines like the Cascadia Subduction Zone, allowing scientists to collect real-time data on tectonic shifts and the buildup of stress along the plates. One of the most notable developments is the integration of real-time seismic data into early warning systems. These systems can detect the first seismic waves of an earthquake and send alerts seconds before the more destructive waves arrive. Although seconds may seem brief, these warnings can provide valuable time for people to take protective actions, such as dropping to the ground, taking cover, and holding on. Furthermore, advances in seismic imaging technology, such as enhanced 3D modeling and satellite-based techniques, allow researchers to better understand fault lines and their behavior. These tools improve the accuracy of earthquake predictions, helping to forecast where and when a large quake might occur. Continuous improvements in seismic monitoring, coupled with predictive models, are helping communities in earthquake-prone regions prepare more effectively for future events, potentially reducing risks and saving lives. The 1700 Cascadia earthquake remained a mystery for centuries, with no written records from the Pacific Northwest. However, clues from nature, including ghost forests, sand layers, and tree ring analysis, helped scientists pinpoint the event's timing and magnitude. Japanese tsunami records also link the disaster to the Cascadia Subduction Zone. These groundbreaking discoveries confirmed the fault's role in the earthquake and highlighted the region's seismic risks. Today, modern technology, including seismic monitoring and tsunami models, along with public awareness campaigns, are crucial in preparing for future megaquakes, ensuring the lessons of 1700 are not forgotten. The 1700 Cascadia earthquake, once a mystery due to the lack of written records, has been unraveled through various clues. Ghost forests, sand layers, and tree ring analysis helped confirm its timing and magnitude, while Japanese tsunami records linked the event to the Cascadia Subduction Zone. These discoveries highlighted the fault's potential for future megaquakes. Today, advancements in seismic monitoring, tsunami models, and public awareness campaigns are helping prepare the region for the next big earthquake. The lessons learned from the 1700 disaster continue to shape modern preparedness efforts, emphasizing the ongoing seismic risks in the Pacific Northwest. The ongoing story of science and safety in the face of nature's power continues to evolve as we learn more about the risks posed by events like the 1700 Cascadia earthquake. Through advancements in seismic monitoring, early warning systems, and public preparedness, we are better equipped to respond to future disasters. However, the unpredictability of natural forces reminds us that while we can prepare, we can never fully control nature. The journey of understanding and safeguarding communities against seismic threats is ongoing, emphasizing the need for continued research, education, and infrastructure improvements to protect lives in the future. Like and subscribe to TimeTales for more historical insights.